2025 Physics Nobel Prize explained. Why quantum tunneling won the Nobel. This is a scientific video which is based on research findings published in famous, peer-reviewed journals and government reports. Please see the reference section available at the end of the video for source papers. Case 1. The New Year's Eve bottles vanishes. It's December 31st. You and your friends toast a year, clink glasses, and responsibly leave several bottles partly full. You go to bed. Next morning, every unfinished bottle has vanished. No sticky notes, no confessions, just absence. Fast forward a month to a get-together friend's place, and plot twist, the very same half-finished bottles are sitting there, acting like they never ghosted you. When everyone side-eyes the host, he shrugs and says, "Relax, I'm writing a paper on quantum tunneling." That's all. No other explanation. Case 2. Platform 9 and 3/4 in Philosopher's Stone. Harry Potter's off to Hogwarts when Hagrid hands him a ticket stamped Platform 9 and 3/4. Harry and friends head straight for a brick wall, and instead of first aid room visit, they glide through to the other side. If you're a muggle, that looks impossible and painful. If you're a wizard, it's just Tuesday. Welcome to the vibe of quantum tunneling. When a universe quietly opens a hidden door in what looks like a solid wall. No spells, just the sneaky rules of the tiny. Jokes aside, let's dive straight into the real subject. If you throw a tennis ball at a wall, it bounces back. If you're an electron, well, you might go straight through. That's quantum tunneling. Nature's small-scale jailbreak, where particles slip past barriers they shouldn't cross. On October 7th, 2025, the Nobel Committee honored John Clarke, Michel H. Devoret, and John M. Martinis for showing that this spooky stunt isn't confined to atoms. It can show up in handheld electrical circuits, too. Translation: The Weird Got Practical. Royal Swedish Academy of Sciences, 2025. Tunneling in plain speak. Think of a hill. In the everyday world, you need enough oomph to climb it. In the quantum world, particles also behave like waves, and the wave doesn't abruptly stop at the hill. A faint tail seeps through. That tail gives a small chance to pop out on the other side. No digging, no dynamite, just quantum rules. This is an armchair physics. Tunneling powers the sun's fusion, underpins scanning tunneling microscopes, and shows up in ultra-sensitive superconducting devices. In the mid-1980s, the Nobel trio and colleagues wired up a superconducting circuit called a Josephson junction and caught tunneling in the act, at a scale big enough to hold, by watching the circuit escape from a stable state it should have been stuck in. They then went further and saw discrete energy steps, the calling card of quantum behavior, in that same circuit. Why this was a big deal? Quantum effects tend to wash out in large, messy systems like us. Yet these experiments showed you can corral many electrons to behave as one giant quantum object, preserve its delicate waveness, and watch it tunnel. No microscope required. Martinis, Devoret, and Clarke, 1987. That insight didn't just tickle philosophers. It nudged us toward today's superconducting qubits, where Josephson junctions are the workhorses of quantum processors. If you want a fine print on how environments help or hinder tunneling, there's a whole playbook. The celebrated Caldera Leggett framework explains how friction and noise can smother quantum behavior long before you plug anything into the wall. Caldera and Leggett, 1983. And researchers still debate how long tunneling takes. Precision experiments keep refining the story. From lab curiosity to useful hardware, the leap from cute quantum trick to chip-level tool is why this Nobel matters beyond bragging rights. Superconducting circuits now exploit those quantized levels and tunneling rates to define, control, and read out qubits. Meanwhile, fresh studies have spotted tunneling in diverse materials and even macroscopic magnetic structures. Evidence of phenomenon isn't picky about where it shows up. On the theory side, people have gotten serious about measuring how macroscopic a system really is. Because calling something macroscopic in quantum land should mean more than kinda big. A note on weird. Yes, tunneling feels like rule breaking. But once you accept that matter is wavy, slipping through thin barriers follows logically, just as a faint sound seeps through a wall. The laws aren't being bent. They're simply quantum. The real magic is engineering. How to keep a quantum system quiet enough to show its subtleties before everyday vibrations and heat knock the wave off its groove. So why the prize now? Because the laureates didn't merely describe tunneling. They built circuits that performed it repeatedly and readably in a way the community could test, tweak, and scale. That tangible bridge from foundational physics to hardware blueprints. Open lanes for quantum sensors and computers. It's the difference between admiring a mountain and forging the path that lets everyone cross. And yes, tunneling still surprises us in living systems, proton hops in DNA, in long-range lab setups, even in design of materials. But that's a feature, not a bug. The 2025 Nobel is a tip of the hat to the moment quantum strangeness stepped onto a silicon stage and took a bow.
Thank you for watching this video. Please subscribe to our channel BP International to watch more videos in the fields of science, technology and medicine.